Perfeito. Eu sou professor no IFT, na Unesp, e também no ICTP-SAIFR. O curso que nós vamos fazer essa semana é sobre fenômenos não lineares em biologia. Então, a primeira pergunta que acho que temos que discutir é sobre o idioma das aulas. O meu português dá para conversar, nós podemos falar, eu entendo para falar para vocês, mas para fazer as aulas, eu acho que vão ficar mais claras se elas forem em inglês. Então, a minha primeira pergunta para vocês é quantos de vocês têm problema entendendo inglês e preferem certamente as aulas serem em português? E quantos de vocês não têm problema para acompanhar em inglês? Então, eu vou pedir para vocês levantar as suas mãos, acho que vão ter aí a opção em reações, levantar a mão. Se vocês certamente não entendem inglês e acham que vai ser muito difícil para vocês acompanhar as aulas se elas forem em inglês. Se esse for o caso de vocês, por favor, levantem a mão e aí decidimos o idioma das aulas. Por favor. Fiquem à vontade, tranquilos, não tem nenhum problema.
Ricardo.
Sim.
Perguntaram no chat se as perguntas podem ser em português.
Sim, vocês podem perguntar em português, eu posso responder em português para vocês, isso acho que não tem tanto problema. O que fica mais difícil para mim é explicar por 2 horas em português, porque aí, quando o tempo vai correndo, eu fico mais cansado, eu começo a falar mais difícil em português, a coisa fica mais engraçada, mas fica mais ruim para vocês aprender. Então, eu acho... Não, o espanhol seria ótimo, mas eu acho que é melhor em inglês, né? Também não vamos ser tão exigentes. Então, vou mudar para inglês agora, mas vocês, por favor, se tiverem perguntas em português, podem fazer em português sem problema nenhum. Eu posso responder para vocês em português, tudo bem? Ótimo. Sim, Davi, tranquilo, espanhol não. So I'm going to switch to English. I'm going to speak not very fast, but if at some point that's a problem, as I said, please tell me, and we will manage. Language shouldn't be a problem. That's the first take-home message here. So the idea that I had in the course when I was organizing it is that all of you, or most of you, come from physics, math, engineering, but you have interest in biology. So I'm guessing, and that's the minimum requirement. Let's say for following the course, and I don't think that's even a requirement, that you had a biology course at some point in your high school in Encino Mayo, or at least you know that living beings reproduce and sometimes they move. That's the only biology that you need to know for following this course. We are going to have 5 lectures. And in the first lecture that is going to be today, we are going to do some brief introduction to what's a nonlinear system. And then we are going to move into biology. We're going to move into ecology, and we are going to study, as you see here in red, one species models. You will see very clearly what I mean by one species model. Then tomorrow we are going to add something a little bit more complicated, but also a little bit more interesting. And we are going to study cases where we have 2 different species in the same place. For instance, imagine a situation where you have a lion and a rabbit, lions and rabbits living together, for instance. Then we are going to, in the third lecture, we are going to study a specific type of models, that is discrete time models, where we will see that instead of measuring time as a continuous variable, we assume that reproduction events happen on fixed time steps. And we're going to see how things change in that case. We are going to see which organisms we can study with these models here in green. And then finally, in the last 2 lectures, we are going to add something a little bit more complex and a little bit more interesting, which is what's the role of space here. So for this first, this is not biology. For these first lectures, we are going to study populations that only reproduce and die. And here we are going to see what kind of interesting phenomena happen when these individuals also move, how can we study those, which kind of models we use, which kind of equations, which kind of techniques we use to study those models, and which kind of new interesting phenomena appear. And here I added some extra, and if we have time, I would like to show you how, even with these few things that we are going to learn this week, you can study a research problem. So I'm seeing some people writing in the chat about Spanish, English. I'm not going to teach in Spanish. If English is hard for you, I can teach Portuguese. Please tell me if you are having problems to follow the course. Please don't be shy. You can write me private if you want. You don't want to raise your hand. But please, I want to make sure that, to me, it's harder in Portuguese, mas eu posso fazer. Então, vamos, por favor, não tenham nenhuma vergonha, nenhum problema para mim. Só levantem a sua mão, ok. Eu vou dar 3 segundos. Se em 3 segundos vocês não falam, eu vou continuar em inglês até o final da semana. Tudo bem? Perfeito. Maria, eu concordo com você. E Viviane, sim, pode falar. Okay. I will speak very, very slowly, okay? If you don't follow, you can ask me in Portuguese and you can write me after the class an email in Portuguese, and I'm happy to talk to you and explain things that were not clear. Okay, so let's start with the first topic that we are going to cover. As I said, we are going to be working with nonlinear systems, and nonlinear systems are everywhere in nature, not only in biology. In biology, they are very abundant because every non-biological system that you can imagine is, by definition, nonlinear. And usually it's very, very complex. In biology, we have many pieces that interact as part of a system. For instance, imagine a population of animals. All the animals are interacting with each other, and they interact in ways that are very complex. And because of those complex interactions, we can have very complex phenomena that happen. And those are the ones that we are going to see. But I want to start with something that we all as physicists, or at least the ones of you that are physicists, are probably familiar with. I'm going to start drawing here a pendulum, a simple pendulum, which is a system that probably most of you know. That is basically a massless particle, a particle with some given mass m, and with some cord without mass that ties it to the wall. So we have here, as probably all of you are familiar with, we have here several forces acting on the pendulum. We have the tension, we have the weight. We can measure the displacement of the pendulum by some angle theta. And then we can decompose the forces in the different radial and vertical planes, as you probably have done in some mechanics course, where here L is the length of this cord. So if you write the balance of forces for this system and you apply Newton's equations, what you will eventually get is an equation of motion for this pendulum that looks like this. So if you haven't taken any mechanics course yet, don't really worry. I mean, the derivation of this will be very clear once you know some mechanics. I'm not going to go into the details because it's not very important. It's not very important for us today. The point that I want to make is that even in a system that is as simple as a pendulum, we get to an equation of motion that is this one here, that is nonlinear. And this equation, we cannot solve it. I mean, we cannot solve analytically the movement for a pendulum. What we usually do is we do what is called the small angle approximation, where we approximate the sinus of theta by the angle itself, and then we get an equation that now is linear, and we can solve it. So basically, this equation, which is now an harmonic oscillator, that for us as physicists is basically the only system that we many times it's the only system that we know how to solve. We still need to do some approximation to get to an equation that is analytically tractable. If we don't do this approximation, there is no way for us to solve analytically something as simple as a ball with some chord and moving around. We can only know the solution when this angle here is very, very, very small. So if this happens with a system as simple as the pendulum, where we only have one particle, and the movement is deterministic, this is for the pendulum. Imagine what can happen for a biological system, for instance, for a population, where we have many particles, let's say n, with n large, and we have stochastic dynamics. The difference between deterministic and stochastic is given by the predictability of these trajectories. So for a pendulum, a simple pendulum, if I know the initial condition and I know the equation of motion, I can tell you where the pendulum will be at every later time. For a population, if I give you the initial number of, for instance, trees in a piece of forest, I cannot tell you how many trees you will have 5 years after, because the dynamics is stochastic, has some random component. And that's going to add a lot of fun things, but it's also going to add a lot of very, very complex and hard to deal with mathematically things. So the main goals that we are going to have in every of the problems that we are going to study are basically 3. So we want to know, as well as here in the pendulum, we said that the nonlinearities appear when this angle theta is large. In biology, we want to know how nonlinearities appear. So what is that is happening in these biological systems that makes them nonlinear? For each of these systems, we are going to be interested in understanding what are the processes of interest and finally, from a more mathematical point of view, we will need to know what are the variables that describe our systems. So what we're going to do is we're going to study different examples. I'm going to show you the biological phenomenon. We are going to build a model to explain that phenomenon. And we are going to identify in each of these examples the answer to these 3 key questions. And all the examples that we are going to study are examples that within the large amount of biological systems that we have are called ecological systems. And more specifically, we are going to study problems that are called in population dynamics. And population dynamics is nothing else but the study of how populations change in size, in location, and in age. For instance, how the individuals get older, how they recover from death, and so on and so forth. So before we go to the first problem, I want to ask you, I ask a lot, so you have to be ready, please, to answer, because this being online is insane, it's super boring, talking to black boxes. So I want to ask you if you have any question up to here of how are we going to approach each of these problems. If you have questions, I don't know if the system allows you. I think you can just unmute yourselves and speak. That to me is easier. Don't worry.
Sorry, one question.
Yes.
Can you guys hearing me, right? Okay.
Mm-hmm.
Okay, yeah. Are you going to make the lecture notes available for us later?
Yes. So I have some slides, some figures here that I'm going to share with you. I'm going, at the end of every lecture, I'm going to put the notes that I write. That's why I'm trying to make them understandable. I'm going to put them in a Dropbox folder so you can read them. And also in that Dropbox folder, I put a material for you to read. Sorry, I forgot to say this, but yes, everything is going to be available for you.
Okay, thank you.
No worries. And something else that I forgot to ask you, if some of you, any of you feels like willing to turn on your cameras and make this more personal, I'm very happy and that would be great. But of course, I don't force anyone. It's just that I realize now that I'm talking to 4 black boxes. So if any of you is willing to and wants, that will be much more fun. Anyway, let's go to the first problem that we are going to study. And the first problem that we are going to study is one of the most important problems in ecology. And of course, we are going to study it from a very, very humble point of view. We're going to be very, very humildes. The problem that we are going to study is biodiversity. So why, when we go to the forest, for instance, to Mata Atlantica or to the ocean, we see so many different types of living beings coexisting with each other and living together, despite they all need the same food to survive. So why is it that we have so many different types of trees if all of them need water to survive? Why is it that there is no a type of trees that takes all the water and kills all the other species? And there was, I mean, this is a question you can imagine that has motivated people for many, many years. They've been trying to understand this for a long, long, long time. But it was in around 1930 when when a researcher started doing a series of experiments in what is called a microcosms, which is basically a bottle with water and sugar. That's a microcosm. You see that biology sometimes has fancy words for things that we can all imagine. And what he did was to grow a population of cells of yeast in that bottle, and he counted how many cells he had in that bottle at the end of some time. For those of you that don't know what yeast is a very, very important microorganism. It's a single cell organism, tiny cells, that is responsible for very important chemical reactions that are behind, for instance, bread, wine, beer. So whenever you are drinking a beer, those of you that like beer, what you are drinking is the fantastic result of yeast's work. So honor given to who deserves it. Anyway, what he did was he took 2 different species of yeast, he allowed them to grow, and he counted the number of cells. And the results of his experiment is what I'm showing you here in this figure. So as you can see, when he took, for instance, this Saccharomyces yeast, he observed that after a while, when the amount of yeast was very low and he didn't measure anything, then the population size started to grow, and eventually it stopped growing. Then he repeated with a different type of yeast, and he observed again this growth initially, and then some saturation. You can see that some very interesting differences in these 2 figures. So for instance, the scale in the volume of yeast is different. The time scale is also different. But the qualitative pattern of this growth is more or less the same. And this is something that is very important in biology, and is something that makes ecological systems very, very attractive for especially those of us that have a background in statistical mechanics. Those of you that already studied the statistical mechanics have read about this idea that the microscopic details of a given system don't really matter to understand the macroscopic patterns. So for instance, if I want to understand the temperature of a bottle with a gas, I don't really need to know if I have molecules with, I don't know, the exact velocity of each molecule. I just get an idea of the distribution, how these velocities look like, and I can work an expression for the temperature of the gas. So this idea is behind many of the models that we are going to study. So let's move back to our blackboard and let's see what do we think may be happening here in this bottle. So what we are going to study now is what as I said, is one species models. And we're going to imagine that we have our bottle. It's going to be green, with, as I said, some liquid with sugar for these cells to reproduce, and we have a bunch of cells. So the question is, how can we explain this pattern that was found in the experiments? We're going to try to do a very simple mathematical model to explain this growth pattern. So as a first naive approximation, as I said, we are only going to assume that these individuals die and reproduce. So I'm going to say that, okay, what is happening in my bottle, if I take a look into this bottle, what is happening here is that I have some cells that are going to be these white balls, and I'm going to say that they are reproducing. And I'm going to represent that by this kind of chemical reaction, which means that one cell is going to divide and going to become two different cells. And I'm going to say that that happens with a birth rate that is B. And I'm going to explain you in a while what I mean by rate, but let's keep that word for now. And then I can also say that as well as my cells are reproducing, they are also dying, and that they are dying with a rate that I'm going to say labeled by D. And this symbol here is nothing else but the empty set, so nothing happens. I have a cell, and all of a sudden it disappears and dies. So this is what is happening microscopically in my bottle. If I'm able to look very, very close to it and I'm able to track every single cell, this is what is happening here. And of course, this is for each single cell, and I have a lot of cells. So what I mean by this B being a per capita birth rate is that every time step dt that we can imagine, a very tiny small discretization of time, I have a probability B times dt of this cell to reproduce. So B is a probability per unit time. And now I'm switching from rate to probability, which is going to be something very, very important for the stochastic nature of these systems. So very simple, what I have is, imagine that I start from one single cell. What I have is that after a time t that is going to be 1 over b, on average, I'm going to have two cells. Then if I wait on average 2 over b, I'm going to have, I'm going to have 3 cells. And I continue this reproduction process, and eventually, in general, I'm going to jump from having n cells to having n plus 1 after a time 1 over nb. This is basically what it means having a per capita birth rate equal to b. Yes, David.
I don't understand why after 2 over b there aren't 4 cells instead of 3, because wouldn't the previous 2 each generate another one?
Yes, that's a very good question. The key point here is that my dt is so small that I only observe one event, because it's not that it's not that all the cells reproduce at the same time. They have a probability per unit time, and I wait a dt that is so small that the probability of having 2 reproductions is dt squared, and that's even smaller. That's the assumption of very small dt. That's a very, very good question.
Okay, thank you.
Thank you. So in general, what I mean is that if I have n particles or n cells, let's speak like with property. If I have n cells, my total birth rate is n times b. This is my total birth rate. At this point, I imagine that for D, which is the death rate, we can follow the same argument and we can get to the conclusion that the total death rate is going to be N times D. But remember that I introduced a term here that is very important. I said probability per unit time. So my system is not deterministic anymore. I will have events, reproductions, and deaths happening with some probability, and then I cannot tell you how many cells I have at the end of the 2 hours. I don't know. If I repeat this experiment, I would get a different way, a different pattern. I probably will get these points looking more or less the same, but one will be upper, one will be downward, because that's noise that is intrinsic in the system. It's not related to your measurement precision. It's intrinsic. It's like measuring radioactive decay. You don't know when the decay is going to happen. Okay? So what this means is that if I define, for instance, a variable to measure this system, that I can imagine that more or less many of you are already guessing that an interesting variable would be the number of particles. This variable is stochastic. This variable does not take us the same value at a given time, every time I repeat my experiment. So what I can give for it is a distribution, a probability distribution function. I can tell you, okay, if you wait for 2 hours, the probability of finding 2 cells is going to be this. The probability of having 15 cells is going to be this. The probability of having 7 million cells is going to be this. But I cannot tell you anything else. It's like measuring a quantum system. This is going to come again in the third lecture, but this has nothing to do with chaos. For those of you that are more curious about dynamical systems and have read about chaos, chaos is a very different thing to stochastic dynamics. We will compare them in the course, so don't get very worried about that for now. So my variable n is going to be a discrete variable that can take values from 0 to up to infinity. It can take any natural number in principle. And if I track it through time, what we will see is that if we start, for instance, if we start with some initial value and we wait for some time, it will jump +1. Maybe we need to wait some time, it will jump +1. Maybe now we need to wait less and it jumps to -1, another -1, +1. It will follow this kind of trajectories. And if I repeat my experiment again, it will start from here and maybe it jumps to here, to here, and to here, and it crosses 0, for instance. And from 0, of course, I cannot recover because I need one cell to reproduce. So how can I describe this system? I have this variable of interest that is n, that changes in time, and n jumps in integer values in jumps of length 1. So for instance, here it jumped +1, here it jumped -1, and there is only transitions from n to n -1 and from n to n +1, right? So in principle, my system has what I can call a transition rate that is from n to n +1, and another transition rate that is from n to n -1. Anyone wants to tell me what are the values of these transition rates? What is the transition that makes me create one cell in my bottle? It's birth, right? So in principle, this is B times n, and this is D times n. So now I kind of get a description for how this n variable changed in terms of birth and rate, which is not very hard. You can imagine as climbing, my population is climbing some stairs. It goes up, it goes down. Birth goes up and death goes down. But now I told you, okay, this is very nice, but I want to know how many cells would I expect after 60 hours, for instance, in these experiments. So I have the question of what is the probability of having n cells at time t. This is the question that I want to address. So let's try to get an equation for this probability. It's the same. Instead of writing my equation for the angle theta in the pendulum, I'm going to write a dynamical equation for this probability. If I know this probability, I have all the information about the system. Because the system is stochastic in nature, but I have the probability of having every single value of n at every single time step. So the probability of having n cells at time t plus dt, imagine that if this is time, I'm here, time t plus dt, and I want to know what is the probability that if I measure the system, I find n cells. The probability of being in this stir, if you want, at this time step is equal to, let me know if you follow me. It's equal to the probability of having n minus 1 cells at time t and climbing up one stir in time dt. So Miguel, yes.
Teacher, could you explain in general lines what you define by stochastic system? I kind of lost here when you speak about it.
So a stochastic system is a system that follows a trajectory that is unpredictable. That's the graph. For instance, the stock market is a stochastic system. Flipping a coin is a stochastic system.
But there's a pattern in the stochastic system, or is totally random?
No. Yeah, that's a very good question. The stochastic system, usually they have some deterministic trend behind, and then they have some noise. For instance, imagine a particle, if you put some small particle in water, for instance, and you, yes?
No, I get it.
So you usually you have this that, for instance, the example of the stock market that I was saying, there is some deterministic behavior in that system that is related to how much money people put in the stock market, how much money they get off, which companies they like, complex things that I'm sorry, but I'm not so interested, so I don't know very well. But there is also, of course, some fluctuations on top of that. There is the effect of how people will react, which we cannot control, for instance. The fact that I will react differently to you, and that made all the weather, for instance. We all say, okay, summer, well, at least in temperate regions with forestations, summer is hot and winter is cold. But sometimes in winter, there is a very sunny day. Sometimes in summer, it rains, even in places with very predictable weather. So there is usually two components, deterministic and some random component on top of it.
Okay, I got
yes,
it.
We're going to see that in a while, actually, now that I remember, and it's going to be very clear, I think, Miguel.
Okay.
So this is the first contribution that we said. We are one stair below, and we jump up. Of course, there is the other case where I am a bit above and I jump down. I'm doing the same. The probability that I am at I have n plus 1 at time t, and then I had some low transition. And then I have a third contribution that is basically that I was at n t and nothing happened. The probability that nothing happened is 1 minus the probability of going down minus the probability of going up. Is this clear to everyone? the probability of going up plus going down plus nothing happening has to be equal to 1. That's normalization of a probability function, probability density function. Okay, so of course, now I have what David said before, which is that I may have processes that are second order. I may have 2 jumps, I may have 3 jumps, I may go up and down, but those I'm going to assume that dt is very small and I'm going to neglect them. I'm going to work with very, very small dt's. Okay, so what I can do next to this equation is, because I'm working with a dt that is very small, I can basically rewrite this in terms of derivatives. So this is a bit hard with Aula Blackboard, but basically you can see, we have this here, we have this term here that can go to the left side, right? And then I can divide all my equation by dt. You can repeat the steps if you want tonight, and you will see that this is what you will get. So as I said, if I take this to the left and I divide everything by dt, this is what I get. And this is equal to the probability of having n minus 1 at time t. And now I have to give expressions for these omegas here. So the transition rate from n to n plus 1, which was jumping up, we said it was b times n. If I am now going from n minus 1 to n, then my transition rate will be b times n minus 1, the reproduction rate per capita times the number of particles that I have. So if I repeat the same for the death term, and for the nothing happening term, this is what I get. So I see yes, you're talking about drunk people in the chat. We are going to talk about that in the 4th lecture. That's the derivation we're going to make it. Just the derivation. We're not going to have cachaça. I'm sorry. So this equation that I got is what is called the master equation. This equation gives me all the information about this birth reproduction process. It's an exact description of the process. If I solve this and I obtain P and P, I am able to fully solve my stochastic process. And that's very important. What's the problem? The problem is that 99% of the times you cannot solve this equation. In this case, we can, because it is very simple. And I refer you to something that is called generatrix. Now I forgot in English. I think it's generatrix function. It's the most common way to solve these equations. And in this case, it works with some fun algebra. But usually it is impossible to solve because this equation has 2 main problems. The first one is that n is a discrete variable. And discrete variables are usually very hard to work with, as we will see also in the 3rd lecture. And the second one is that this equation is usually nonlinear. In our case, it's linear, and that's good. That's why we can solve it. But usually it's nonlinear, and that's a mess. So we need to find strategies to work with these systems when we cannot solve the master equation analytically. So the question is, how can we work with this mess? So there are 2 ways. The first one is numerical simulations. So we can put this birth-death process in our computer and we can run it. We can get like these very fancy trajectories here. And we can get a lot of them and we can try to calculate averages, variances, fluctuations. But that's a bit of brute force because I don't get general ideas. I like to know where I am in the parameter space, and with that, I don't know it. And the second thing that we can do is to find analytical solutions for some properties of P and T. And this is what we are going to focus on. We are going to see how we can work our way to get some idea of how, sorry, how these equations are, how these probability distribution functions work. This is, of course, as I said, a not very ambitious goal, but sorry, you will see that many times is the only thing we can do. So we are going to get expressions for something that is called the moment of P and T. And I'm going to define the kth moment as the sum from n to infinity of n to the power of k, P, and T. This definition of moment is because n is a discrete variable. If n were a continuous variable, then you have to change the sum by an integral, and you have to change the domain of the sum by the proper domain of integration that you want. So, among all the moments that you can work, k equal to 1, k equal to 2, 3, 4, whatever you want to use, we are going to work with the first moment, which is basically, by definition, this thing here, that for those of you that are more familiar with probability and with random variables and stochastic processes, this is the mean number of particles. What do I mean with this? What I mean by this is that this mean number of variables is going to give me, let me see, how can we do this? So imagine that I have these 4 realizations of my birth-death process. If I now focus on a given time, let's say tau, if I get P of n tau for different n, I get a histogram, for instance. And I get the probability of having 1 particle, the probability of having 2, the probability of having 3, I don't know. I get some different probabilities for each of the values. What I'm going to calculate now is an equation for the mean value of, sorry, for the mean value of this histogram here. So basically it's the same as running these trajectories 1,000 times and getting some smoother average over all the different stepwise functions. This is what we are going to try to do. So how can we do that? So we have our, let's try to recover the master equation. So we have our master equation here, and we have also the definition of the mean value of n as the sum from 0 to infinity of n, p, and t. So what I can do is, because I have p and t in many places, I will multiply in both sides of my equation by n, and I will sum from 0 to infinity. So this is what I'm going to do. And I'm going to do that on the right and on the left side. And I think, okay, yes, I did it right. I just put the square to n times n square. So what can I do now? I have here this n times the time derivative of p of n over n doesn't depend on t. So I can say I can switch the order of the time derivative and the sum in a way that I can get the derivative over time of the mean value of n. Okay, and the only thing I'm doing is to put this inside the time derivative because n does not depend on time. And now I have something that is slightly more complicated to deal with. I have these terms here. I have these terms here where you can see that I have n minus 1 here and n here. And that's a problem, no? Because my definition of the mean value, what I want is n and n. So what can I do? What I'm going to do is I'm going to take this term. Let's see, how can I do this without being very messy? Okay. I'm going to take this term and I'm going to work it on a different page. So what I have is, maybe if I rearrange a little bit, it's going to be a bit more easy. Let's see, sorry. I have n minus 1, and here I have a b, and I have p n minus 1 t. This is what I have. What I'm going to do now is I'm going to call my index n, I'm going to call it m. Sorry, I'm going to change variables, and I'm going to say n minus 1 is equal to m. I'm just going to rename. And what I get is that the sum from n minus equal to minus 1 to infinity of m plus 1 times m pm t. Okay, the only thing I'm doing is if n minus 1 is m, then n is equal to m plus 1, and I redo these things. The next thing that I can do is, because p of minus 1t is equal to 0, remember that my my variable is always positive because I'm counting a number of cells, and the number of cells cannot be negative. I can just change the limits of my sum, because if I'm summing 0 plus a series of numbers, the only thing I'm doing is removing the first one because it's 0. And then what I get is the same, n plus 1 m p of m t. And here I have a b. And now the final thing that I have is, okay, I have some index that is a blind index, is summing, and I call it m. But why I call it m? I mean, I could have called it r. I could call it a butterfly, or I could have used a tree. I mean, that's not a big deal. So I undo my change and I say m is equal to n. So basically what I have is n equal to 0 for infinity of n plus 1 n p n t. Okay? And now what I gained by doing this is that I moved from something where I had pn minus 1 in my sum. Now I have p of n, which is what I want, because it's how I'm defining the moments of my distribution. So I can just put this here. So you can work, you can do the same thing for all the other for all the other terms, and have some fun to see that you understood this. I'm not going to repeat, so we can move forward. So basically what we have for the depth term is d n minus 1 n P and T, and then we don't do anything for the nothing happening term. Okay. So remember that this part, so just in case whenever you get the notes, is like an inset here. So this is now my my equation. Let's put some green, for instance, and let's see what can we do with it. So the first thing that we see is that, for instance, here I have b n squared p and t, and here I have the same term, but with different sign. So in principle, I can eliminate this with one of these, and I can eliminate one of these with with the other one of these. You can expand if you want the parentheses, and you will see that that this vanishes. And at the end, what you get is this equation here. Let me. Okay. So what you get is the derivative of n versus t is equal to b infinity n p and t minus d n p and t. And of course, this is b minus d, the mean value of n, which is a function of time. Okay, so what do we have? What we have is that we moved from this more complicated master equation that we said that many times we cannot solve to a single ordinary differential equation for the mean number of cells that at least more times I will be able to solve. In this case, of course, my equation is extremely simple, especially for those of you that have a physics background or a math background, and I can integrate it. And I'm sorry because I'm already losing part of the notation. And you can get that this is equal to the exponential of b minus dt. This is the solution for the mean number of particles. So what do we mean by this solution is that if we plot the mean number of cells as a function of time, starting from some initial condition, if b is larger than d, my population will grow exponentially, exponentially, exponentially. If b is smaller than d, my population will die exponentially. And if b is equal to d, in the critical case, nothing will happen. Right? This is what this equation is telling me. Sorry. So imagine that you have a situation where b is larger than d. If you repeat your experiment and allow these cells to grow many times, in one of the cases, you probably will get something like this. In another case, you will probably get something like this. Sometimes you may even observe something like this. You may even observe that your population dies. But if you run this a million times, and in every time step you calculate the mean of these 1 million experimental realizations, what you get is a nice, smooth exponential curve. So this is related to your question before, Miguel. There is a kind of deterministic trend behind that, in this case is given by the mean number of cells, but on top of that I have my fluctuations that are blurring and are hiding my result. But now let's take a look well, now we have the model. Remember that our idea was to explain this experimental result. For those of you that know how the exponential functions work, I'm assuming that something is not working fine. But in principle, we have a parameter that is b minus d. And I can try to do some statistical tests to see how can I fit an exponential curve over these points. More or less what you guys do in the lab, in the laboratory in I don't know, in the experimental courses in physics. If you do that, this is the best you can get. Okay, the beginning, it was decent. I could take some points, but then things don't really work. I have to say that this is not a real exponential fit. This is not a real fitting of an exponential function to the whole data set, because then it will do something like this. But what I was trying to bring the idea that these exponentials will work very well in the short time, but then they break down. There's no way for us to, because you know that the exponential curves, they grow to infinity or they go to zero. There's no way to stabilize in this kind of region. So the question is, what are we missing here? And I want to stop 5 seconds to see if someone tells me what do they think we are missing here. Any idea?
Could the B and D change in time, possibly?
B and D changing in time would be a good hypothesis. That's right.
The carrying capacity of the environment.
We have here someone that knows about ecology. The current capacity of the environment, I'm going to take that as well. BD changing in time. Very good. Pedro, is your name? Pedro?
Yes, yes.
Change in time. Some new word came that is going to get very clear now. What does it mean? Current capacity of the environment. Any other hypothesis? So what is happening actually is both things that you guys said, and Miguel and Pedro are happening. What is happening is that we are not recovering what is called the current capacity of the system, which is the maximum number of cells or the individuals that the system can host. And we are not doing that because B and D effectively are changing in time, and we are not considering that. We are saying, no matter if I have 1 trillion cells in my bottle, they continue to reproduce. And that, even if we don't know anything about biology, but just by physical arguments, that's impossible. If I have a bottle that is finite, I cannot have 10 to the power of 36 cells in my bottle, right? So I'm missing something there. And what I'm missing is actually no linearities. So what's happening in my bottle, let's bring it from the first slide, because I was very proud of my picture. So what is happening here is that what we are missing is that at some point, when this environment gets very, very crowded, cells are going to fight with each other to get the sugar. So we can represent that by saying that at some point, the system is going to get so crowded that cells somehow are going to collide with each other. They are going to find each other. And from 2 cells, we are going to have 1 cell. And this is going to happen at a rate gamma. The name that this ecological interaction has is competition. Cells are competing for a resource that can be a space, that can be the sugar, can be a space and sugar, can be many things. And that is limiting the maximum number of cells that we can have in the bottle, and is giving rise to what Pedro calls the current capacity that we will see in a while, how it emerges. So what we are going to have is, what we have to do now is we have to define this rate that you see is different to these 2 here on the left, because here I have 1 cell, but here, for the reaction to happen, I need 2 cells to find each other. which is not happening in the other ones. In the other ones, I'm super happy and I divide. Here, I'm super happy and someone finds me and I fight. And that encounter is not incorporated in our model. So how can we incorporate it? So we are going to take a little bit of a bigger look into here. Let's see. So we're going to imagine that we have here a part of our bottle with a lot of cells, many of them. And we're going to focus on one that we are going to call the green one. Green is always a nice color. So the green cell. This green cell I'm going to now see what is the probability that this green cell finds any other cell. And to do that, I have to make a hypothesis. So if my cells are imagined like that they are atoms that are placed in the positions of a solid, they won't find each other. No, if they are trees and I have a tree in Sao Paulo and I have another tree in Rio, there is no way for them to find each other. If they are closer, they cannot find each other either. But let's be extremist. But if everyone is moving around, there is some chance that they will find each other. And if I assume that my molecules are perfectly mixed, as we, for instance, assume in ideal gases, then the probability that this cell, this green cell, finds another cell is going to be proportional to the density of cells. Right? So I can imagine that this is all homogeneously mixed. I have an immense cloud of cells. So the probability that I interact with any other is going to be given by the density of cells around me. This is the law of mass action that maybe some of you know already from thermodynamics or statistical mechanics, depending on the course. Of course, something that is very interesting that, for instance, came to all the newspaper and to many of you probably read is what happens if this is not well mixed. You have the example, for instance, in COVID. What is the effect of social distancing or physical distancing in epidemics spreading? The effect is related to assuming that instead of being well mixed, I become a solid, an atom of a solid, and I stay in my house. I break the probability of encountering with all my friends, and I break the probability of transmission. The idea is the same, okay? So, of course, the only reason why I chose here n-1 is because the green cell cannot collide with themselves, with herself, okay? I have n-1 possible candidates to collide. Then, of course, I need to add here some encounter probability that, for instance, can give you an idea of the velocity of the cells. So what's the probability per unit time of actually encountering? So there is two options. Sorry, there is two contributions to these encounters. One is the strength or the rate at which it happened, and the other one is how crowded the environment is around me. And then the final step that I have to take to define, sorry, this is gamma proportional to this. The final step that I have to make to change this proportionality by an equal is to consider that the green one is not green because it's a privileged one. In principle, any cell can be the green one. So what I have is n times n-1 v gamma 0. And probably doesn't make sense, but to me, it hurts on my eyes. So gamma 0 goes in front. So this is the encounter, the rate at which this reaction happens. So what is the very important thing that you, any of you, yes, Miguel, kind of mean free path, kind of. As you increase the number of cells, the mean free path is smaller. Rafael, you're asking, could it be a limit cycle due to non-linearities? We will touch on that tomorrow. In this case, we only have a species, so we don't have limit cycles, but we could have. I'm very sorry that I'm answering the questions a bit late, but I'm getting used to the multi-screen thing. So going back to this result, who wants to tell me what is the main difference between this gamma and between the rates that I had before. Maybe we can write this way, changing a little bit the notation. So who wants to bet what is the main difference?
Depends on the volume.
First one, it depends on the volume. That's a very important observation. If I have a bigger system with the same number of particles, the probability of encountering the system is more dilute, and the probability of encountering is smaller. Smaller. Something else?
It's not linear.
It's not linear, exactly, Yaderson. I'm very sorry if I pronounce your names wrong, but there is a reason for which we are doing this we are doing that in English. It's not only teaching, it's also getting used to names. Yaderson, yes, that's right. It depends on V, and it is non-linear in N. So now we have a non-linearity. Let's see how the movie changed when we have this non-linearity. And you will allow me to approximate this by gamma 0 n squared over V. Okay, I'm going to take NB to be large. That's going to make things a little bit easier. And you are going to allow me also to redefine gamma 0 in a way that it absorbs the volume. Okay, nothing very hard to follow. It's just that I don't like, the less I have to write, the less mistakes I make. Great, so now we can repeat all the calculation that we did. We can repeat the steps we follow to write the master equation. Sorry, I'm not going to do that, don't worry. That's for you to do at home if you feel like. And I will get a new master equation that this time is nonlinear. Why is it nonlinear? Because my rates are nonlinear now. One of them is nonlinear. And if you repeat the calculation, I'm going to write just the result so we can discuss it. Here I made a mistake. If you repeat the calculations and you get to a different solution, the probability that you have the right one and I have the bad one is 1. So that's going to be deterministic, and don't be very, I'm trying to copy just because of that. So this is what you would get if you repeat all the steps we did. You define the rates, you say that the probability of reaching n particles is having 1 and going down, having n minus 1 and going up, and so on and so forth. This is the master equation that you get. This master equation now, as we said, has one nonlinear term here and one nonlinear term here. Yes. And these nonlinearities make this system already impossible to solve. So notice the difference between just considering these new encounters. Now the master equation, I cannot solve it. Before I could. You can read about that. Now I can't. So now this approach that I took to define the moments of my distribution and try to get a deterministic description of my system in terms of some macroscopic variable makes more sense, because now I have no access to any analytical information of the master equation. But we can do the same. We can define, the moments of P and T. And specifically, the first moment is the one that we like the most. And we can repeat the same. We can multiply here by n and sum from 0 to infinity on the left, on the right. You will need to redo the indices algebra carefully, not to make any mistake. So it's some practice. Although there is a way to generalize all these things and to get a recipe for a closed master equation, it's good to practice it so you get some your hands on the algebra. if you do that, let's leave here the step indicated. If you do that, you will get to again, you will get to an ODE for the mean number of particles. That is going to be B minus D and T minus, I think here is gamma and square. Good. So now I again have an ODE for the mean number of particles. What's the difference now between this ODE and the previous one? Can I solve it as easily as the other one, or do you see any problem for me to work with this, or what's the problem here? Any idea? Well, I see a very important difference actually. So what I see is that I have here the mean number of particles, right? I have it here as well. But what do I have here? Here I have the second moment. Yes, the variance term. I have the second moment, right? So if I want to solve this, I need to write an equation for this. I need to come to my master equation and I have to do this, apply the definition of the second moment, and I have to get it. If you do this, unsurprisingly, what you will get is that this equation depends on the third moment of n. So what's the problem? That then I have to come to my master equation and I have to write another equation for the third moment, and so on and so forth. And if this never ends, basically. You get a hierarchy of infinite ordinary differential equations coupled with each other that you cannot solve, because how am I going to solve something if I cannot even like write it down, no? So what can we do? Let me write it here so you infinite hierarchy of coupled ODEs. What would you do if you face this? Imagine that you are in an exam. If you don't pass the exam, you don't finish your graduação, or you don't get the access to the master, or I don't know, or you don't get I don't know, you get anything, but you want to solve it because you like solving problems. What would your imagination tell you to do? Any idea? Any clue?
Numerically.
Numerically is a good idea, Miguel. If you have a computer, it's a very good idea. If you don't have a computer, remember that we're going to do everything sorry, that was fine. We want to do it with a pencil. So I don't know, but at least now that I read the solution, what I would do is to say, okay, I don't know very well how far this is going to get, but I'm going to do this. What is this approximation telling us? This approximation is telling us that we are going to neglect the fluctuations. No, we are going to assume it's equal to 0. Sorry, this is equal to 0, which is standard deviation. This approximation is called the mean field approximation. For those of you coming from physics, yes, this is yet one more mean field approximation. I think it's everywhere in physics. we don't have so much imagination to put names. Yes, Rafael, very well. Sorry, I have to focus more on the chat to see the answers. Rather than neglecting, approximating the second moment by the square of the first. If you are interested in not losing so much information, something that you can do is called, and I will open here a note, is called the Gaussian approximation. Where you would get an ODE for, sorry, is everyone comfortable if I use this notation for the time derivative? The point, I think we are all right. I would get my equation for the first moment. I would get my equation for the second moment. And instead of truncating it with one equation, I truncate it in the second. I will approximate my third moment as a linear combination of the second and the first, I think. I don't remember the expression, but it's basically, for those of you that are more familiar with statistics and distributions, for the normal distribution, for the Gaussian distribution, you can write everything in terms of the first and the second moment. So basically what you do is to rewrite the third moment in terms of the second and the first, and then you get one more piece of information. You get two equations and you work in a two-dimensional phase space with n and n squared instead of only with n. We are going to be, as I said in the beginning, very humble, and we are going to stop in this first equation, which is already, you will see, is already interesting enough. So what can we do to this equation? Sorry. I'm going to anticipate Miguel's answer again. Well, again, no, for the first time. And of course, solve it numerically is one thing, which is always a good idea to get an idea of general behaviors of the equation. It's always an option. What's the second idea, second thing that you guys think we could do? Yes, Rafael, it's a kind of, yeah, it's basically a moment closure approximation is the technical name, where you closure either in the first moment or in the second and you get more information. Well, I guess the second option that we can do is to solve it analytically. I was waiting for the mathematician of the group to reveal their identity. You can imagine that sometimes it's not that easy. Solving these equations analytically, of course, as the equation gets more complicated, it's an ODE, a nonlinear ODE. That's not possible always. In this case, we can, and you can play with it tonight, or you can put in Mathematica, or you can text in Wikipedia logistic model. By the way, this is the logistic equation. And you will see that it has an analytical solution that you can get. But the third thing that we can do, that is actually what we are going to do in these last 30 minutes that we have, is to try to do some qualitative analysis of the behavior of the equation. And what I mean by qualitative analysis will become very, very clear in a while. But before that becomes clear, let's jump to our experiment back. So now what I'm showing you in this nice figure is basically the same that I did before, try to fit some of the solutions of this equation. So basically, as I told you, I can solve the logistic equation analytically. So what I'm doing is taking the solution and finding the combination of parameters. If I call B minus D, I call it R, and gamma. The combination of these two values that give me a better fit to my experimental data. Of course, here I will get R1 and gamma 1, and here I will get R2 and gamma 2, right? different values because the quantitative details of my model, of my experiment are different. But you can see that the agreement, the way I can explain my data with this simple model is very, very good. So that gives me an idea of the characteristic time scales of the system, of the, as Pedro said before, of the carrying capacity of the system, which is nothing else but this saturation value. And so on. So for those of you that are more familiar with this type of models and have read about them before, probably the notation that I'm using and the way that all this appear is new to you, because sometimes these models appear derived in a very phenomenological way that I don't like. Probably as a physicist, I really like this micro-macro connection because I came from statistical mechanics. But if you have read them written in this way, is basically the same. This is just a way of rewriting things, as you can probably see from the way I got it. You can, this is R, and you take it out, and you rewrite K. It's just a way to rewrite things in a way that the fixed points of the system, the stationary state values, the values of the population size in the stationary state appears very visual, because we will do it now and you will see. But it's the same, okay? The equation, the solutions, everything is the same. It's just a matter of reparameterizing the equation. Okay, so let's. Yes, Leticia, that's a very, very good question. Very, very good question. What is the physical or biological property of the system that makes our mean field approximation valid? That's the question here, right? Because how can I do these approximations, in which limits, when they are valid, when they are not? The mean field approximation works very, very well when the population size is large. So the fluctuations are a contribution to this general trend, because remember that I'm neglecting the fluctuations. And it also works very, very well when the, how can I explain that? Yes. So let's go back to the to the first model that we studied, this very simple exponential growth. This was for the mean number of particles. And remember that I said, okay, if B is equal to D, then I don't get dynamics, right? Because this is 0 and this is constant. That's not true, okay? In this case, this approximation doesn't work, and I will have fluctuations that will always kill my system, because it will always move around, and then eventually when it hits 0, it goes to 0. The system has what is called an absorbing state. It's an state where it gets frozen. Fluctuations don't get it out from there. So when we have combinations of parameters in which the deterministic component of the movement is too weak, as for instance here it vanishes because the both rates are the same, then the system is fully driven by fluctuations. In those cases, the mean field approximation is terrible. Why? Because the mean field approximation basically consists on neglecting the fluctuations. So when the population size is large, usually the mean field approximation works very well, or when we have a clear deterministic trend behind the dynamics, it also works. Both work. But I think we will come back to this tomorrow. And if I don't make that answer more clear tomorrow, Leticia, please make it again, because we can discuss on that tomorrow with a lot of information that is going to be very helpful. Okay, so let's take let's take the equation again. And now, as part of our qualitative analysis that we said we are going to do, let's try to find the fixed points of this equation, the values of n in the stationary state when I don't have when my dynamics freezes. So in that case, basically, what I have is an algebraic equation that I can. Sorry, I'm a little bit afraid that at some point I'm going to make a mistake, so I'm just going to call this R already, and R is equal to B minus D, and it's going to be easier. So R in minus T minus gamma and square T is equal to 0, which means that we have two stationary states that I'm going to call N star that are equal to 0 or equal to R over gamma. This can be, we can call it the trivial state, where basically it's the extinction. And this one is, as Pedro pointed out before, the carrying capacity. But now, okay, I know that if I start my system with some parameters and I start with some number of cells, cells will start reproducing, they will start dying until they either hit this this n star value or this n star value. And what we want to calculate now is which is the value that they are going to hit. So is there a way for me to say, given these parameters, I'm going to go to the current capacity or I'm going to go to the extinction? Can I do that? And the way to do that is with something that is going to appear many times in this course, which is called a linear stability analysis. The linear stability analysis is something that is very, it's a mathematical technique that is very useful for nonlinear systems, that basically consists on assuming that we are in the stationary state. We are in one of these two fixed points. We kick the population size a little bit. We kick the solution, the value a little bit, and then we see if it goes back to the stationary state or if it leaves it. If the system goes back to the stationary state, then we say that that fixed point is what is called stable. And if it goes away, then the fixed point is unstable. Okay? It's given by how the system responds to perturbations to that system. So what we are going to say is that my solution N is going to be N star plus epsilon x with epsilon much smaller than 1. Epsilon is very, very small. And we are going to see how this perturbation behaves. So our equation is not so hard. It's basically we have, and I'm going to remove the, well, I'm going to keep them. So it's a quadratic equation, not very hard, but in principle, I can do it, my calculation very generally. I can say that this right side of my equation is some function of n. Right? So basically, what I can do is, and now I can, sorry, to make then the notation easier, let's assume that we remove this from the notation. I think that's going to help. So basically what I have is n dot is equal to f of n. And if I use this form for n, basically what I get is that n star plus epsilon x is equal to f n star plus epsilon x. Okay. Now, this is a very, very simple calculation for those of you that have more physics or math background. But for those that you don't, I think it's also, we can follow it. So this n star, basically I obtain it saying that the derivative of n with respect to time was equal to 0, right? And I obtain n star. So the time derivative of n star is equal to 0 because this, by definition, is a stationary state. Doesn't change with time. So what we can do is epsilon is constant. It's a very small number. The derivative of x with respect to t is equal to this, this f here. This f here, remember that epsilon is very small, so then I can do a Taylor expansion of the function. And I will truncate it in the first term, because, well, in the second, in the linear term. That's why it's a linear stability analysis. Okay, so who wants to tell me what is the value of this term here?
0.
0. Very well, Lucas. Very good. 0. Why? Because it's my condition for a stationary state. This is equal to 0. So now I have this epsilon that goes away, this goes away, and at the end what I get is a linear ODE for the temporal evolution of my perturbation. The solution of this basically is going to tell me that x is proportional to some exponential of f prime of f prime evaluated at the fixed point times t. So how can I get the stability of these fixed points? If f prime, sorry, this is me going too fast. If f prime evaluated at n star is negative, what happens to this exponential? It decays, right? So my perturbation gets smaller, it decreases. So we said that in that case, the fixed point was going to be stable. On the contrary, if f is larger than 0, my solution is going to be unstable. Okay? So let's go back to our system. In our system, we have that Fn. Sorry, let me put the titles because if not, it's going to be very hard for you to. In our case, f of n was equal to Rn minus gamma n squared. F prime of n then is equal to R minus 2 gamma n. Right? Okay. So if n squared, n star is equal to 0, this means that f prime of n squared is equal to R. So if R is positive, which means that B is larger than D, then n star equal to 0 is unstable. And if R is negative, which means that B is smaller than D, then n star equal to 0 is stable. What does this mean? This means that if the rate at which my cells divide is larger than the rate at which they die, the extinction state is unstable. As soon as I put 3 cells, 4 cells, 2, then my sorry, my population size will take off and will grow. If the death is larger than the birth, then it will crash. I think that's very intuitive, but it's important to understand this math because things will get a bit more complicated tomorrow. What is very also I want you to think about is that this stability condition is all given by B and D. Why? Because we are working with linear stability analysis, so it makes sense that it's dominated by the linear terms of the equation because we are working in the limit of a small n, right? As you can see from this equation, from our equation, when n is very small, this term is the dominant one, and as n grows, this one starts taking off and starts blocking the exponential growth. That's a very qualitative way of understanding how this is working. We have this linear term that makes the growth rate, this f function, positive, but eventually n gets very large, these terms starts claiming its quadratic power and starts stopping the growth until we stabilize in the current capacity. So what happens with the other fixed point, with n star equal to r over gamma, which I'm going to call k, so you get an idea of how to connect with this other notation. In this case, you will see that the rule is, the result is basically the same, the opposite. If r is smaller than 0, sorry, if r is positive, then and n star equal to k is stable. And if r is negative, then is unstable. This means that if I have a population that is in the current capacity, and my death rate and my birth rate is larger than the birth rate, and I kill a little bit my system, then the population will get extinct. So what is very important is that this is if I put a small perturbation on the fixed point. The fixed points are fixed points always. They freeze the dynamics. They equate this Fn to 0. So if I don't move them away, if I don't move my system away from it, there is no way I will take the system off from it. That's the stationary state. That's a definition. Then it's unstable or stable. For those of you that have already taken mechanics courses, this is related to minima and maxima of potential. We can do a mechanical analogous to these dynamical systems. We can define a potential for these terms, and if you work all that way, you will see that n equal to 0 is a maximum of potential when B is larger than D, and the current capacity is a minimum of the potential, and you can get things in the same way. And actually, it's a very common way to approach these problems. I want to finish a bit earlier so we can have some questions, but I just want to finish with a different way of attacking this stability analysis. So now it was very nice because we could calculate n star analytically, right? But what happens if I can't? Imagine that, I don't know, I have some hyperbolic tangent, or I have a fifth order polynomial that I cannot obtain the roots analytically. Then what's going to happen to me? I'm lost. Do I have some hope? The answer is that there is hope. There is always hope. And there is ways to do that of course will not provide us with analytical results, but will give us some idea of the stability of these points. And I want to finish with that. It's going to be about 3 minutes. I don't think it's going to take us more. So if we cannot find those solutions, what we can do is what is called a graphical analysis, which is basically what you guys probably do if you want to plot a function, for instance, and you cannot find the roots. you try to do some graphical solution of these equations. So imagine in our case, for instance, we have this Fn, and we want to obtain Fn equal to 0. Of course, what we can do, for instance, is to say, okay, this means that Rn minus gamma n squared is equal to 0, which means that Rn is equal to gamma n squared. Okay, so then I can, for instance, do my graphical analysis. I can plot Rn. I'm going to use blue. This is Rn if R is positive. And I can similarly, let's use pink. I can plot my parabola, gamma n squared. And in the places where they cross each other, I have fixed points. How do I know the stability of the fixed points? Well, sorry, this is n, and this is, well, this is the Rn and gamma n squared. If this is my n star equal to k fixed point, on the right of this fixed point, the parabola is larger than is greater than the straight line, which means that this Fn is negative. It means that I will go in this direction. On the left side is the other way around, right? Because the straight line is above the parabola, and the straight line is positive, and here is negative. So basically, this fixed point is going to be stable, and if you repeat the calculation, this one is going to be unstable. This is kind of, I mean, it's possible, but I don't like it a lot because, well, you have to think. I know you probably guys, you're smarter than I, and it's not such a big deal. But sometimes one can make mistake. One can make mistakes if the functions are not as easy as a parabola and a linear function. So I like it more. This one that this other graphical approach that I'm going to show to you now. That is basically you represent f of n as a function of n, which in our case is going to be this parabola if R is positive and gamma is positive. Gamma is always positive by definition, by the way. But if R is positive, this is how this R of n is going to work. And of course, the fixed points are going to be the values of n where this function crosses 0. Now the stability to me is much more intuitive because to me it's easier to think in terms of comparing with 0. So here f of n is negative, right? So this means that n will change to the left. Remember that here this is f of n, and therefore it's also the derivative of n with respect to t. So if I am here, the derivative of n with respect to t is negative, right? Because f of n is negative and the derivative of n with respect to t is also negative, and therefore n will decrease. If we are here following the same reasoning, this is positive, the derivative of n is positive, so I move to the right, and therefore this point is stable, because if I am here and I take n to the left, to the right a little bit, it will recover the original position. Following the exact same way of thinking, you can see that this is here negative, and therefore, sorry, this is here positive, here is negative because there is another change in the sign of f of n, and therefore this is unstable. This fixed point is unstable, and this fixed point is stable. for those of you that are thinking a little bit ahead, that probably are many of you, you can already see that this approach is also very nice, because if f of n is continuous, which most of the times is, because we have a growth rate that most of the time is going to be continuous, then if we know the stability of one fixed point, because the stability is related to the changes in sign of f of n, I have all of them, because I only alternate stable and stable, stable and stable, right? So that's another way of doing this very easily. Just calculate one and then I move forward with all of this. This works in one dimension. We will see tomorrow that in 2 dimensions it's not that easy, but it's much more fun. And something else, again, that I leave for you to do today is to if you want to define this f of n as the minus derivative of a potential, and you then can relate these fixed points to minima and maxima of the potential, and everything works as a mechanical kind of mechanical kind of system. Okay. So this is what I wanted to tell you today. As I said, let me see that I didn't forget any picture. As I said, we still have a few minutes, so if you have questions, that can be either doubts about the calculations today, or I don't know, I saw that before someone asked about the emergence in biological systems. So if there are more kind of questions like that don't really go into what we discussed today, you can make them now. And just in case some of you feel shy to ask with this recording, I think I will stop the recording now.